The universe is not dying the way we thought it would. For 27 years, we believed the cosmos would race apart forever, stars dimming into darkness across an endless expanse of frozen void. But in 2025, the data changed. Dark energy, the mysterious force that has been tearing space itself apart for billions of years, is weakening. The expansion is slowing down. The universe has already entered a new phase, and we never noticed. This means everything we calculated about the end of existence is wrong. The heat death is off the table. A new fate awaits us, one that was dismissed as impossible just 3 years ago. If you want to see how science rewrote the story of forever, hit that like button and subscribe. Tell me in the comments, do you think time is a circle or a line? Now settle in, relax, and let the journey begin. The shift happened quietly. Researchers at the Dark Energy Spectroscopic Instrument in Arizona spent 3 years mapping 15 million galaxies and the blazing cores of distant quasars. They traced how space stretched across 11 billion years of cosmic history. The patterns they found did not match the model we have trusted since 1998. Dark energy was supposed to be constant, a fixed property of the void that would push galaxies apart with relentless, unchanging force. Instead, it is fading. Its density has dropped by 10% over the last 4.5 billion years. The acceleration that once seemed eternal is slowing. This is not speculation. The evidence comes from 3 independent lines of observation. The first is the ancient sound waves frozen into the fabric of space, ripples from the early universe that act as cosmic rulers. The second is the light from exploding stars, supernovae that reveal how fast space was expanding when their light began its journey to us. The third is the warping of light by gravity, the way distant galaxies bend the path of photons and betray the shape of the invisible web that holds the cosmos together. When you combine all 3, the conclusion is inescapable. Dark energy is not a cosmological constant. It evolves, it weakens, and if it keeps weakening, the future we imagined vanishes. Young-Wook Lee, an astrophysicist at Yonsei University in South Korea, led the team that pushed this discovery into the open. His work, published in November 2025, states something extraordinary. The universe is not accelerating anymore. It has already transitioned into a phase of deceleration. We are living through the turning point, the moment when the engine driving cosmic expansion begins to sputter and fail. Lee's analysis shows that this shift is happening faster than anyone predicted. Dark energy is not just fading slowly over trillions of years. It is collapsing rapidly enough that the consequences will arrive in cosmological terms soon. What does this mean for the end? If dark energy continues to weaken, expansion will not just slow, it will stop. And once it stops, gravity takes over. Every galaxy, every star, every atom will begin to fall back toward the center. The universe will contract. This is the Big Crunch, the mirror image of the Big Bang, where all of space collapses into a singularity of infinite heat and density. 2 years ago, this scenario seemed implausible, a relic of outdated cosmology. Now, it is back on the table. The timeline is uncertain, but the mechanism is clear. The force that has been holding the universe open is failing, and when it fails completely, everything falls. For nearly 3 decades, we lived with a comfortable answer. The universe would expand forever, growing colder, darker, emptier as the eons passed. This was the heat death, the slow fade into an infinite frozen void where stars burn out one by one and galaxies drift beyond each other's reach. It was a lonely ending, but it felt certain. The data from 1998 had spoken clearly. Observations of distant supernovae revealed that space was not just expanding, but accelerating, pushed apart by a mysterious force called dark energy. Albert Einstein had predicted this force nearly a century earlier when he introduced the cosmological constant, a number that represented the hidden energy woven into the fabric of the void itself. The Nobel Prize confirmed it. Dark energy was real, powerful, and seemingly eternal. It made up 70% of everything that exists, and its repulsive force outmatched gravity across the larger scales. Galaxies would continue separating faster and faster until the cosmic horizon shrank around each island of matter, isolating them in bubbles of space that could never be crossed. Eventually, trillions of years from now, the sky would go dark. The last stars would flicker out. the universe would reach a state of maximum entropy, a uniformly cold expanse where nothing moves, nothing changes, nothing happens. This was the future we accepted. It was built into textbooks, simulation models, and the fundamental equations that describe how space behaves. But there was always another possibility. It was older than the heat death theory, dating back to 1922 when Russian physicist Alexander Friedmann derived the equations that govern cosmic expansion. His mathematics showed that the fate of the universe depends on a single factor: density. If there is enough matter, gravity can halt the expansion. If gravity wins, the universe does not expand forever. It contracts. This is the big crunch. Space collapses back on itself. Galaxies merge, stars ignite from the heat of compressed radiation, and everything rushes toward a singularity where time and space cease to exist. For decades, this scenario seemed unlikely. Most measurements suggested the universe lacked the mass needed for gravity to reverse the expansion. The discovery of accelerating expansion in 1998 seemed to close the door on the big crunch entirely. Yet the theory never disappeared. It lingered in the equations, a dormant fate waiting for the numbers to shift. Some physicists kept exploring what a contracting universe would look like. They calculated timelines, describing how galaxy clusters would merge first, then individual galaxies, then stars. The cosmic background radiation, now a faint glow left over from the Big Bang, would brighten and blueshift as space shrank. The temperature would climb. In the final moments, atoms would disintegrate, nuclei would shatter, and black holes would consume everything around them before merging into a single gravitational abyss. At the very end, the universe would become an infinitely dense, infinitely hot point, indistinguishable from the state it was born in. The Big Crunch carried with it another idea, even stranger. If the universe could collapse back to a singularity, perhaps it could bounce. The Big Bounce hypothesis suggests that the Big Bang was not the beginning of time, but a transition, the moment when a previous universe finished its contraction and rebounded into expansion. This creates a cyclic model where the universe endlessly repeats itself, oscillating between Big Bangs and Big Crunches across infinite time. Some versions of this model propose that the cycles are identical, replaying the same history forever. Others suggest that each cycle is slightly different, with new constants and forces emerging after every bounce. Until recently, these ideas were considered speculative, elegant in theory but unsupported by observation. The assumption was that the cosmological constant was positive, meaning dark energy would always push outward. That assumption is now in question. The cracks appeared long before anyone noticed. For years, cosmologists measured the universe and found small discrepancies that did not make sense. Distant supernovae looked slightly fainter than expected. Galaxy clusters seemed distributed in patterns that the standard model struggled to explain. The cosmic background radiation, that ancient light from the first moments after the Big Bang, showed subtle features that hinted at something missing in the equations. These were not dramatic anomalies. They were whispers, inconsistencies buried in the noise of measurement error and statistical uncertainty. Most scientists assumed they would fade with better instruments and larger datasets. Instead, they grew stronger. One of the most persistent problems was the Hubble tension. Two different methods for measuring how fast the universe expands produced two different answers. When scientists looked at the early universe using the cosmic microwave background, they calculated one expansion rate. When they looked at nearby galaxies using supernovae as distance markers, they got a rate that was roughly 9% higher. 9% may sound small, but in cosmology, it is enormous. Both measurements were precise. Both had been checked and rechecked, yet they refused to agree. This suggested that something fundamental was wrong with the model everyone was using. Then came the first hints from the Dark Energy Spectroscopic Instrument. In April 2024, the DESI collaboration released results from their first year of observations. They had mapped 6 million galaxies, tracing how the universe expanded over the last 10 billion years. The data showed ancient sound waves frozen into the distribution of galaxies, ripples from the early universe that serve as cosmic rulers. When the team analysed these patterns, they found something unexpected. The data fit better when dark energy was allowed to change over time rather than remaining constant. The difference was not definitive. but it was significant enough to make the researchers pause. They called them hints, not conclusions. The statistical measure of confidence was 3.9 sigma, meaning the odds of getting this result by chance if the standard model was correct were roughly 1 in 7,000. The scientific community reacted cautiously. Hints like this had appeared before and disappeared with more data. Cosmology is filled with anomalies that turn out to be errors in calibration, unknown sources of systematic bias, or just bad luck in how the data happen to cluster. The DESI team emphasized this uncertainty. They presented their findings as a puzzle, not a revolution. But behind the careful language, something was shifting. Other groups began reanalyzing their own data with the possibility of evolving dark energy in mind. The Dark Energy Survey, which had spent 5 years photographing galaxies from a telescope in Chile, found similar patterns. When they combined their observations with DESI's results and data from the cosmic microwave background, the preference for changing dark energy persisted. The evidence was piling up. By March 2025, the picture had sharpened. DESI released results from 3 years of observations covering nearly 15 million galaxies. The hints became evidence. The statistical significance rose to 4.2 sigma, roughly 1 chance in 30,000 that the result was a fluke. Dark energy's density appeared to have dropped by 10% over the last 4.5 billion years. This was not a slow drift buried in uncertainty. It was a measurable decline, consistent across multiple independent datasets. The ancient light of the cosmic microwave background agreed with it. The positions of distant supernovae agreed with it. The way gravity bent light from faraway galaxies agreed with it. When researchers deleted any one of these datasets and reanalyzed, the conclusion remained. Dark energy was weakening. The warnings had been quiet, but they were real. The universe reveals itself through dying stars. Type 1. A supernovae, the explosions of white dwarf stars that have accumulated too much mass from nearby companions, burn with a brightness so consistent that astronomers call them standard candles. When you measure how bright they appear from Earth and compare that to how bright they truly are, you can calculate their distance with astonishing precision. When you measure how their light has been stretched by the expansion of space, you can determine how fast the universe was growing when that light began its journey. These two numbers together tell you the history of cosmic expansion across billions of years. In 1998, 2 teams studying distant supernovae found something shocking. The universe was not just expanding but accelerating. Galaxies were moving apart faster now than they were in the past. This meant something was pushing against gravity, a mysterious force that came to be called dark energy. For the next 25 years, every new supernova measurement confirmed this conclusion. The acceleration seemed relentless, unchanging, eternal. Dark energy appeared to behave like a cosmological constant, a fixed property of space that never weakened or strengthened no matter how much the universe grew. But the supernovae had more to say. When scientists combined the latest supernova data with observations from the Dark Energy Spectroscopic Instrument and measurements of the cosmic microwave background, a different pattern emerged. Dark energy's influence did not remain constant across time. It was stronger in the distant past and weaker in the more recent universe. The effect was subtle, a shift of only a few percent, but it showed up consistently across multiple independent datasets. When researchers tested different models to see which one best fit all the observations together, the model where dark energy evolves performed better than the standard cosmological constant. The implications rippled outward. If dark energy weakens over time, the acceleration driving galaxies apart will eventually slow. If it slows enough, expansion will stop entirely, and if expansion stops, gravity will pull everything back together. The fate of the universe hinges on this balance between dark energy and matter. For decades, scientists believed dark energy would dominate forever, driving the universe toward a cold, empty heat death. Now the data was pointing toward a different ending. The Big Crunch, once dismissed as impossible, had returned as a serious possibility. Young-Wook Lee and his team at Yonsei University pushed the analysis further. They studied 2,000 supernovae spanning 11 billion years of cosmic history. They combined this with gravitational lensing data, measurements of how light from distant galaxies bends around massive clusters of matter. They included observations of ancient sound waves frozen into the distribution of galaxies. When they put all the pieces together, the conclusion was stark. The universe has already entered a decelerating phase. The expansion is no longer speeding up, it is slowing down. This is not a prediction for the distant future, it is happening now. We are living through the moment when the cosmic engine shifts into reverse. Dark energy is not matter. It is not light. It is not a force like gravity or electromagnetism. It is something stranger. Dark energy is the name we give to the mysterious pressure that fills the void itself, pushing space apart from the inside. Imagine an invisible spring woven into every cubic meter of emptiness, a tension that grows stronger as the universe expands because more space means more spring. This pressure does not pull or attract. It repels. It drives galaxies away from each other with a force that overpowers gravity across the largest distances. For decades, scientists modeled dark energy as a cosmological constant, a number that Albert Einstein introduced into his equations in 1917. Einstein called it lambda, a fixed property of space-time that never changes no matter how the universe evolves. In this model, dark energy has a constant density. As space expands, new dark energy appears to fill the new volume, keeping the pressure steady. This seemed to match the observations from 1998, when astronomers discovered that distant supernovae were farther away than expected. The universe was accelerating. Lambda explained it perfectly. But the latest data suggests lambda is wrong. Dark energy is not constant. It evolves. Its density has dropped by approximately 10% over the last 4.5 billion years. This means dark energy is weakening. The pressure that drives cosmic acceleration is fading. If this trend continues, the repulsive force will eventually lose its grip on the universe. When that happens, gravity will take over, the expansion will stop, and then the universe will begin to contract. The discovery came from the Dark Energy Spectroscopic Instrument, a robotic observatory perched on a mountain in Arizona. Over 3 years, it mapped nearly 15 million galaxies and brilliant quasars stretching back across 10 billion years of cosmic history. The patterns in their distribution revealed ancient sound waves frozen into the fabric of space, ripples from the early universe that act as cosmic rulers. By measuring how these patterns have stretched over time, researchers reconstructed the history of expansion with unprecedented precision. When they combined this with data from exploding stars and the warping of light by gravity, the picture became clear. Dark energy's influence has been declining. The statistical confidence in this result is 4.2 sigma. This means that if the standard model of cosmology were correct, the odds of seeing this pattern by random chance would be roughly 1 in 30,000. That is equivalent to flipping a coin 15 times and getting heads every single time. The evidence does not come from a single measurement or a single telescope. It comes from multiple independent sources that all point to the same conclusion. The cosmic microwave background, the oldest light in the universe, supports it. The distribution of supernovae supports it. The gravitational lensing of distant galaxies supports it. When researchers remove any one of these datasets and reanalyze, the preference for evolving dark energy remains. The finding is robust. What this means for the future depends on how fast dark energy continues to weaken. If it declines slowly, the universe could keep expanding for trillions of years before the contraction begins. If it drops rapidly, the turnaround could happen much sooner. Some theoretical models suggest that dark energy might even plunge below zero, becoming attractive instead of repulsive. This would accelerate the collapse, pulling the universe back toward a singularity within tens of billions of years rather than trillions. The data cannot yet tell us which scenario is correct, but the direction is clear. Dark energy is losing strength. The force that has been tearing the cosmos apart for billions of years is failing. The equations that govern the universe are not gentle. They allow for violent endings, catastrophic transformations, and fates we cannot easily imagine. For a century, physicists have known that space itself obeys mathematical laws, and those laws contain something called the cosmological constant. Albert Einstein introduced it in 1917 as a fudge factor to keep his equations balanced. He later called it his biggest blunder. But in 1998, astronomers realized the constant was real. It represented dark energy, the force driving cosmic acceleration. For 2 decades, everyone assumed the constant was positive. A positive constant means eternal expansion, a universe that grows forever. But the new data changes the sign. Henry Tai, a physicist at Cornell University, took the latest measurements from the Dark Energy Survey in Chile and the Dark Energy Spectroscopic Instrument in Arizona and fed them into the equations. What he found was stark. The cosmological constant is not positive, it is negative. A negative constant means something entirely different. It means the universe will not expand forever. It will reach a maximum size, stop, and then begin to contract. This is not speculation. It is what the math demands when you plug in the numbers. Tai published his results in the Journal of Cosmology and Astroparticle Physics in October 2025. The conclusion was unavoidable. The universe will end in a big crunch. The timeline is surprisingly precise. Tai's model predicts that the universe is 33 billion years old from birth to death. We are currently 13.8 billion years into that lifespan, approaching the midpoint. The expansion will continue for another 11 billion years, reaching its peak size around 24 billion years from now. At that moment, the universe will stop growing. For a brief instant, space will hang still, balanced between expansion and contraction. Then gravity will take over. The collapse will begin slowly at first, galaxies drifting closer together over billions of years. But the process will accelerate. 20 billion years from now, roughly 33 billion years after the Big Bang, the universe will compress back into a singularity. Everything that exists will converge into a single point of infinite density and infinite temperature. This is the big crunch. The model relies on a hypothetical particle, a field of extremely low mass that behaves like a cosmological constant early in the universe but loses strength over time. This particle mimics the properties of dark energy in the early epochs, driving the acceleration we observe. But as the universe ages, the particle's influence fades. Eventually, its contribution becomes negative, flipping the cosmological constant from repulsive to attractive. Once that happens, the universe is doomed to collapse. The beauty of the model is that it fits the data remarkably well. It explains why dark energy appears to be weakening, why the Hubble tension exists, and why the universe seems to be transitioning into a new phase. Not everyone is convinced. Some physicists argue that the data is not yet strong enough to overturn decades of established cosmology. The statistical significance of evolving dark energy is 4.2 sigma, which is compelling but not definitive. A 5 sigma result, the gold standard for discovery in physics, would require more observations. The next round of data from the Dark Energy Spectroscopic Instrument will arrive soon, along with measurements from the European Euclid Space Telescope and NASA's Nancy Grace Roman Space Telescope. These missions will map the universe with unprecedented precision, measuring billions of galaxies and tracing the evolution of dark energy across cosmic time. If the pattern holds, if dark energy continues to show signs of weakening, the case for a big crunch will become undeniable. But if the new data shifts, if dark energy stabilizes or behaves differently than expected, the equations could point to another fate entirely. For now, the math says the universe will collapse, and the clock is ticking. The heat death was the promise of a slow, peaceful fading. It offered a quiet end, trillions of years away, where the universe would not explode or collapse but simply run out of steam. Stars would burn through their fuel and wink out. Galaxies would drift so far apart that light from one could never reach another. Space would expand faster than light could travel, isolating every cluster of matter in its own bubble. Eventually, the universe would reach a state called maximum entropy, where all energy is evenly distributed and nothing can happen anymore. No motion, no change, no time, just an infinite expanse of frozen darkness. This fate emerged from the second law of thermodynamics, the rule that says disorder always increases. Every process in the universe generates waste heat, spreading energy into more chaotic forms. A star converts hydrogen into helium and radiates light. That light scatters into space, warming dust and gas until it dilutes into faint infrared glow. Eventually, the glow fades to nothing. The energy still exists, but it becomes so spread out that it cannot do any work. This is entropy, the measure of how disordered a system has become. In a closed system, entropy always climbs toward a maximum. When it reaches that peak, everything stops. In the heat death scenario, the universe would take an unimaginably long time to reach this final state. The last ordinary stars would die in 100 trillion years. The only sources of light would be white dwarfs, fading embers left over from dead suns, and brown dwarfs, failed stars that never ignited. These would cool gradually over quadrillions of years. Black holes would be the last holdouts, massive objects where gravity is so strong that nothing escapes, but even black holes evaporate. Through a process called Hawking radiation, they slowly lose mass by emitting particles into the void. The larger the black hole, the slower it evaporates. Supermassive black holes, the giants at the centres of galaxies, would take 10 to the 100th power years to disappear. After that, nothing remains. The appeal of the heat death was its inevitability. As long as dark energy remained constant, pushing galaxies apart at an accelerating rate, there was no way to avoid it. The discovery of cosmic acceleration in 1998 seemed to seal the universe's fate. Dark energy made up 70% of everything that exists. Its repulsive pressure dominated gravity on the larger scales. No force in physics could overcome it. The conclusion was stark. The universe would expand forever. Entropy would rise forever. Eventually, space would become so dilute and so cold that nothing interesting could ever happen again. But the heat death relied on an assumption that is now in question. Dark energy was supposed to be constant. The cosmological constant was supposed to stay fixed. If that assumption is wrong, if dark energy weakens over time, the entire scenario collapses. The latest observations from the Dark Energy Spectroscopic Instrument and the Dark Energy Survey suggest that dark energy is not constant. It is fading. Its density has dropped by 10% over the last 4.5 billion years. If this trend continues, the repulsive force driving cosmic expansion will eventually lose its grip. Gravity will take over. The universe will stop expanding, and when expansion stops, the heat death becomes impossible. Instead of drifting apart forever, galaxies will begin to fall back together. The end will not be cold and quiet, it will be hot and violent. The Big Crunch replaces the heat death. There is a fate worse than collapse. There is a scenario where the universe does not fade quietly or crunch violently, but tears itself into oblivion. This is the Big Rip, the nightmare ending where dark energy does not weaken but strengthens. Instead of fading over time, the repulsive force accelerates out of control. Space expands faster and faster until it rips galaxies apart, then stars, then planets, then atoms. Everything that exists is shredded down to fundamental particles. Even space-time itself tears at the seams. The Big Rip depends on a specific kind of dark energy called phantom energy. Unlike the cosmological constant, which remains steady, phantom energy grows stronger as the universe expands. Its density increases instead of staying fixed. This creates a runaway effect. The more space expands, the more phantom energy appears, and the more phantom energy appears, the faster space expands. The feedback loop spirals out of control until expansion reaches infinite speed. At that point, nothing can hold together. Gravity becomes irrelevant. Electromagnetism becomes irrelevant. Even the strong nuclear force, which binds protons and neutrons inside atomic nuclei, cannot resist the ripping force of space itself. The timeline for a Big Rip is shockingly short compared to other cosmic endings. Some models predict it could happen in as little as 22 billion years from now. That is only 8 billion years after the Sun dies. The process would unfold in stages. First, galaxy clusters would dissolve as their member galaxies drift too far apart for gravity to hold them together. This would happen roughly 1 billion years before the end. Then individual galaxies would shred, their stars flung into the void. This would occur about 60 million years before the rip. 3 months before the finale, solar systems would disintegrate. Planets would separate from their stars and tumble into darkness. 30 minutes before the end, planets themselves would explode as the space between their atoms stretched faster than molecular bonds could handle. In the final fraction of a second, atoms would tear apart. Electrons would rip away from nuclei. Protons and neutrons would shatter into quarks. Then space-time itself would rupture, and everything would cease to exist. The Big Rip seemed plausible when dark energy was first discovered. Early measurements of cosmic acceleration left open the possibility that the force-driving expansion could be dynamic, changing over time in ways that might intensify rather than fade. Some theoretical models of dark energy, particularly those involving exotic fields with unusual properties, predicted exactly this behavior. Physicists even gave these models names like quintessence and phantom energy, exploring their mathematical consequences. For a while, the Big Rip was considered one of the leading candidates for the ultimate fate of the universe. But the latest data rules it out. The observations from the Dark Energy Spectroscopic Instrument and other surveys show that dark energy is weakening, not strengthening. Its density is dropping by about 10% every 4.5 billion years. This is the opposite of phantom energy. A force that weakens over time cannot accelerate expansion to infinity. It cannot rip the universe apart. Instead, it will eventually lose its battle with gravity. The Big Rip is off the table. The universe will not tear itself to pieces. It will either expand forever in a slow fade toward the heat death, or it will stop expanding and collapse into a big crunch. And the current evidence is leaning toward the crunch. The Big Crunch is the mirror image of the Big Bang. Space does not expand forever but reaches a maximum size, pauses, and then begins to collapse. Galaxies that have been racing apart for billions of years slow down, stop, and reverse direction. Gravity, the weakest force on quantum scales but the most powerful across cosmic distances, finally wins its war against dark energy. Everything that has been spreading outward through space for nearly 14 billion years begins to fall back together. The universe contracts, and as it shrinks, it heats. The end is not cold like the heat death. It is fire. The collapse would unfold over billions of years. At first, the changes would be subtle, visible only through precise measurements of distant galaxies. Their light would shift toward the blue end of the spectrum instead of the red, indicating that they were moving closer rather than farther away. Galaxy clusters would begin to merge, drawn together by their mutual gravity. The cosmic web, the vast network of filaments and voids that structure the universe, would tighten. Empty regions of space would shrink. Dense regions would grow denser. Over time, the gaps between galaxy clusters would close. As the universe continues to contract, the pace accelerates. Individual galaxies collide more frequently, triggering bursts of star formation as clouds of gas compress and ignite. The night sky grows brighter as galaxies crowd together. The cosmic microwave background, that faint glow of ancient light left over from the Big Bang, begins to warm. Right now, it hovers at roughly 3 degrees above absolute zero. In a contracting universe, that temperature rises. The radiation blue shifts as space shrinks, concentrating its energy into shorter, hotter wavelengths. Eventually, the background radiation becomes visible light. Later still, it becomes scorching ultraviolet and then X-rays. The temperature climbs relentlessly. Stars burn brighter and die faster as the ambient radiation heats them from the outside. Planets lose their atmospheres, stripped away by the intensifying radiation field. In the final million years, space becomes too hot for solid matter to exist. Planets vaporize, stars dissolve into plasma, galaxies merge into a single glowing soup of particles. Black holes, those gravitational prisons from which nothing escapes, begin to consume everything around them. They grow enormous, swallowing stars and gas clouds by the millions. Eventually, the black holes themselves merge, forming ever larger singularities. In the last moments, the universe resembles the conditions it was born in. Atoms disintegrate into protons, neutrons, and electrons. Protons and neutrons shatter into quarks. The 4 fundamental forces of nature, which separated shortly after the Big Bang, begin to merge back together. Space collapses faster than light can travel. All the matter and energy in the universe converges on a single point. The temperature soars toward infinity. Density becomes infinite. Time itself warps and breaks. At the singularity, the laws of physics cease to function. Everything that exists is compressed into a state of zero volume and infinite curvature. This is the Big Crunch, the final convergence, the collapse of all things back into the void from which they came. The Big Crunch might not be the end. There is a scenario where the universe does not collapse into oblivion but rebounds, where the singularity becomes a gateway instead of a grave. This is the Big Bounce, the idea that the universe has died and been reborn countless times before, each cycle ending in a crunch and beginning with a bang. Time does not start with our Big Bang. It stretches infinitely into the past an endless chain of births and deaths, expansions and contractions, universes stacked on universes like waves crashing on a shore that has no beginning. The bounce requires exotic physics. In standard cosmology, nothing can stop a singularity once it forms. When all the matter and energy in the universe converge on a single point, the density becomes infinite, the temperature becomes infinite, and space-time itself breaks down. General relativity, the theory that describes how gravity warps space, cannot handle infinite curvature. The equations collapse into nonsense. But quantum mechanics, the theory that governs the smallest scales, might save the day. At extremely high densities, quantum effects become important. These effects could create a repulsive force strong enough to halt the collapse and reverse it, turning the crunch into a bounce. One model that achieves this is called ekpyrotic cosmology. In this framework, our universe exists on a three-dimensional membrane floating in a higher dimensional space. There is another membrane nearby, another universe separated from ours by a tiny gap in the extra dimensions. Every trillion years or so, the two membranes collide. The collision releases enormous energy, heating both universes to unimaginable temperatures and triggering what we perceive as a Big Bang. After the collision, the membranes drift apart and the universes expand and cool. Eventually, they are pulled back together by forces in the higher dimensions, and they collide again. The cycle repeats endlessly. From our perspective, each collision looks like the beginning of time, but it is just one event in an eternal sequence. Another version of the bouncing universe comes from Roger Penrose, the physicist who proved that black holes contain singularities. His model, called conformal cyclic cosmology, suggests that the far future of the universe becomes the distant past of the next one. After all the stars die and all the black holes evaporate, the universe enters a state dominated entirely by massless particles like photons. In this state, time loses meaning. Without mass to mark the passage of events, there is no way to distinguish one moment from another. Penrose argues that this timeless state can be mathematically transformed into the hot, dense conditions of a new Big Bang. The old universe does not collapse. It simply transitions, seamlessly and eternally, into a new cycle. The evidence for a bouncing universe is indirect but intriguing. Some physicists point to anomalies in the cosmic microwave background, subtle patterns that could be imprints left over from a previous cycle. Others argue that the smoothness of space, the fact that the universe looks nearly the same in all directions, is easier to explain if the Big Bang was not the beginning. A bouncing universe has time before the Big Bang to smooth itself out through repeated cycles. The latest data on dark energy does not prove the bounce, but it makes it plausible. If dark energy weakens enough to allow a big crunch, then the conditions for a bounce could be met. Whether the universe actually rebounds or collapses into a true singularity depends on physics we do not yet understand, but the possibility remains. The end might not be final, it might be a doorway. The universe has offered us a menu of fates. For decades, the heat death seemed certain, an inevitable slide into frozen darkness where stars burn out and galaxies drift beyond reach. The Big Rip lurked as a nightmare scenario, a catastrophic tearing where space itself shatters. The Big Crunch sat dormant in the equations, dismissed as implausible, until dark energy showed signs of weakening. The Big Bounce promised eternal return, cycles repeating without end. Now the data has spoken. The field has narrowed. The evidence points toward two possible endings. The first is the heat death, the scenario where dark energy stabilizes. If the weakening of dark energy slows or stops, if it settles at a positive but diminishing value, the universe could still expand forever. The acceleration would decrease, but expansion would never halt. Galaxies would continue separating, more slowly than in the past, but relentlessly nonetheless. Over trillions of years, the cosmos would cool, darken, and thin until nothing remains but isolated black holes evaporating into faint radiation. This fate requires that dark energy reach a floor, a minimum value below which it cannot drop. Some theoretical models predict exactly this behavior. They suggest that dark energy will fade to a small but non-zero constant, weak enough to allow structure to persist longer than previously thought, but strong enough to guarantee eternal expansion. The second is the Big Crunch, the collapse back into fire. If dark energy continues weakening at its current rate, or if it plunges below zero and becomes attractive, the universe will stop expanding. Gravity will take over. Everything that has been flying apart for nearly 14 billion years will begin to fall back together. This scenario matches the latest observations from the Dark Energy Spectroscopic Instrument and the Dark Energy Survey. The data shows that dark energy's density has dropped by approximately 10% over the last 4.5 billion years. If this trend continues, the cosmological constant will flip from positive to negative within the next several billion years. Once that happens, collapse becomes inevitable. The timeline depends on the exact behavior of dark energy. Henry Tye's model, published in 2025, predicts that the universe has a total lifespan of 33 billion years from birth to death. We are currently 13.8 billion years into that span. Expansion will continue for another 11 billion years, reaching maximum size around 24 billion years from now. After that, the universe will contract for roughly 9 billion years before collapsing into a singularity at the 33 billion year mark. Other models give different timescales. Some suggest the crunch could happen sooner if dark energy drops faster than expected. Others predict longer lifespans if the weakening slows, but all models that incorporate the latest data on evolving dark energy point toward the same conclusion. The Big Crunch is back on the table. The choice between heat death and Big Crunch hinges on measurements we cannot yet make with certainty. The statistical confidence in evolving dark energy is 4.2 sigma, compelling but not definitive. A 5 sigma result, the gold standard in physics, requires more observations. The next generation of telescopes will provide those observations. The Dark Energy Spectroscopic Instrument will continue mapping galaxies for years to come. The European Euclid satellite, launched in 2023, is already surveying billions of galaxies across the sky. NASA's Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will measure the expansion history of the universe with unprecedented precision. These missions will determine whether dark energy truly weakens, stabilizes, or behaves in ways we have not yet imagined. Within a decade, we will know which fate is ours. The clock has started. For the first time in human history, physicists have calculated a specific date for the end of everything. The universe has a lifespan, a beginning, and an ending measured in numbers we can write down. 33 billion years from the Big Bang to the Big Crunch. We are currently 13.8 billion years into that journey, nearly halfway to the finish line. The expansion that has defined cosmic history for almost 14 billion years will continue for another 11 billion, reaching its peak around the year 24 billion. Then the universe will stop growing, and then it will collapse. The model comes from Henry Tye, a physicist at Cornell University, and his collaborators. They used data from the Dark Energy Survey and the Dark Energy Spectroscopic Instrument to constrain the behavior of dark energy over the last 10 billion years. What they found was that the cosmological constant is not positive, as decades of theory assumed. It is negative. A negative cosmological constant means the universe cannot expand forever. Gravity will eventually win. The math is unambiguous. If the model is correct, the universe will reach maximum size at roughly 69% larger than it is today, about 7 billion years from now. After that, contraction begins. The collapse will be slow at first. For billions of years, galaxies will drift closer together at speeds too small to notice without instruments. The sky will gradually brighten as galaxies converge. Stars will continue to form and die. Black holes will continue to grow, and life, if it still exists, will carry on under skies growing steadily more crowded. But around 10 billion years from now, the contraction will accelerate. Galaxy clusters will begin merging violently, their collisions igniting waves of new star formation. The cosmic microwave background will heat up, shifting from radio waves to infrared, then visible light, then ultraviolet. The universe will begin to glow. In the final billion years, the collapse becomes catastrophic. The temperature of the background radiation climbs above the boiling point of water, then the melting point of iron, then the surface temperature of the sun. Planets vaporize. Stars swell and burst as external radiation overwhelms their internal structure. Galaxies dissolve into vast clouds of plasma. Black holes merge into ever larger singularities, growing exponentially as they devour the collapsing matter around them. In the final moments, roughly 33 billion years after the Big Bang, space collapses faster than light can travel. All the matter and energy in the universe converges on a single point of infinite density. Time ends. The big crunch arrives. This timeline carries enormous uncertainty. The model depends on assumptions about dark energy that have not been confirmed. The negative cosmological constant is speculative. Other models, using the same data, predict different outcomes. Some suggest the universe will expand forever, slowing but never stopping. Others propose that dark energy will stabilize at a small positive value, leading to a heat death trillions of years in the future rather than a crunch in 20 billion. The difference hinges on measurements that current telescopes cannot yet make with certainty. But the very fact that scientists can propose a specific timeline, testable and falsifiable, marks a turning point in cosmology. The fate of the universe is no longer abstract philosophy. It is physics, and the answer is within reach. Gravity never stopped fighting. For nearly 14 billion years, it has been losing the war against dark energy, watching helplessly as galaxies race apart and space stretches beyond its reach. But gravity is patient. It is the oldest force in the cosmos, woven into the fabric of space-time itself. It bends light, crushes stars, and holds galaxies together even as dark energy tries to tear them apart. And now, as dark energy weakens, gravity senses its moment. The balance is shifting. The invisible hand that shapes the universe is tightening its grip. Dark energy works by creating negative pressure, a repulsive force embedded in the void that pushes space apart from the inside. For billions of years, this pressure dominated the large-scale structure of the universe, overpowering gravity across distances greater than a few hundred million light-years. Galaxy clusters drifted apart. The cosmic web stretched thinner. Empty voids expanded faster than matter could fill them, but dark energy's strength depends on its density. As the universe grows, the density of matter drops because the same amount of mass spreads across more space. Dark energy was supposed to remain constant, maintaining its density even as space expanded. That assumption kept gravity on the losing side. The new data destroys that assumption. Dark energy is not constant. Its density is falling. Over the last 4.5 billion years, it has dropped by approximately 10%. If this trend continues, dark energy's grip on the universe will weaken further. Eventually, its repulsive pressure will fade below the attractive pull of gravity. When that happens, expansion will slow. The galaxies rushing away from each other will decelerate. Their motion will not stop immediately. Momentum carries them forward for billions of years, but the distance between them will grow more slowly with each passing eon. The universe will coast toward maximum size. Around 11 billion years from now, the expansion will halt. The universe will reach its peak diameter, roughly 69% larger than it is today. For a brief moment, nothing will move. Galaxies will hang motionless in space, balanced between outward momentum and inward pull. But the balance cannot hold. Gravity does not rest. It tugs relentlessly, bending space-time toward mass, drawing objects together with a force that grows stronger as distances shrink. Once expansion stops, there is nothing to resist. The universe will begin to contract. The collapse will start slowly. At first, galaxy clusters will drift closer together at barely perceptible speeds. Over millions of years, the gaps between them will narrow. The cosmic web will tighten. Filaments of dark matter and gas that connect galaxy clusters will shorten and thicken. Empty voids will shrink. The universe will grow denser, and as it grows denser, gravity strengthens. The contraction accelerates. What begins as a slow drift becomes a steady fall, and the steady fall becomes a plunge. In the final 8 billion years, the universe will collapse from maximum size to a singularity. Space will shrink faster than light can travel. Time itself will warp and break. Gravity, the weakest force on the smallest scales, will claim absolute victory on the largest. Everything will fall. The universe will hold its breath. 11 billion years from now, space will stop expanding. For a single moment, frozen in cosmic time, galaxies will hang motionless against the dark. They will have been racing away from each other since the Big Bang, carried by the expansion of space itself for 24 billion years. But momentum cannot last forever when gravity pulls the other way. The outward rush will slow, decelerate, and finally cease. The universe will reach its maximum size, roughly 69% larger in diameter than it is today. Then the direction will reverse. This turning point is not arbitrary. It emerges from the balance between dark energy and matter. Dark energy drives expansion by exerting negative pressure, pushing space apart from the inside. Matter and gravity pull inward, trying to collapse space back together. For the first 9 billion years after the Big Bang, matter dominated. The universe expanded, but the expansion slowed because gravity was stronger. Then, around 4 billion years ago, dark energy took over. Its density remained constant while matter's density dropped, and this shift caused expansion to accelerate. Galaxies began separating faster, but if dark energy weakens over time, as the latest data suggests, the balance will shift again. The mathematics of this transition are precise. When the universe reaches maximum size, the scale factor, the number that describes how much space has stretched since the Big Bang, will peak and then begin to fall. Right now, the scale factor is increasing by about 7% every billion years. In the distant future, that rate will slow. The scale factor will grow by 6% per billion years, then 5, then 4. Eventually, growth will drop below 1%. Then it will stop entirely. At that moment, the universe will have expanded by a factor of roughly 1.69 compared to its current size. A galaxy that is 1 billion light-years away today will be 1.69 billion light-years away at maximum expansion. Then the distance will start to shrink. The transition will be imperceptible to anyone living through it. There will be no sudden jolt, no cosmic signal marking the moment. Galaxies will not stop moving abruptly. Their velocities will taper off gradually over millions of years, slowing so smoothly that no instrument could detect the change in real time. Only by comparing observations separated by tens of millions of years would astronomers notice that distant galaxies had shifted from redshift to blueshift, that the light stretching toward longer wavelengths had reversed and begun compressing toward shorter ones. This would be the first sign. The universe would no longer be expanding, it would be contracting. From that point forward, the fate is sealed. Gravity will dominate completely. Dark energy, if it still exists, will be too weak to resist. The contraction will accelerate as galaxies draw closer and their mutual gravitational attraction grows stronger. What begins as a slow drift will become a steady fall, and the steady fall will become a plunge toward annihilation. The turning point is the hinge of cosmic history, the moment when the universe pivots from life to death, from expansion to collapse, from the age of stars to the age of fire. And according to the models, we are already halfway there. The reversal will be subtle at first. After 11 billion years of outward motion, galaxies will begin drifting back toward each other at speeds measured in centimeters per second. Across millions of light years, this amounts to almost nothing. A galaxy cluster that is 500 million light-years away will close the gap by a few hundred kilometers per year. Human lifetimes would pass without visible change. Civilizations could rise and fall without noticing that the cosmos had shifted direction. Only the most precise instruments, measuring the redshift of distant galaxies over decades or centuries, would detect the transition. The light from those galaxies, once stretched toward the red end of the spectrum by expanding space, would begin shifting back toward blue. Blueshift is the signature of approach. When an object moves toward you, the waves of light it emits compress, shortening their wavelength and shifting them toward the blue. Right now, nearly every galaxy beyond our local group shows redshift, proof that space is carrying them away. But in a contracting universe, this reverses. Distant galaxies will blueshift. The farther away they are, the stronger the blueshift. Astronomers living billions of years from now will measure this effect and realize that their universe is shrinking. They will see galaxy clusters closing the gaps between them, voids collapsing, and the cosmic web tightening like a net pulled taut. Over the first billion years of contraction, the changes will remain modest. The universe will shrink by only a few percent. Galaxies will drift closer, but not close enough to collide. Stars will continue to form in gas clouds. Planets will orbit their suns undisturbed. The night sky will grow slightly brighter as galaxies move nearer, but the difference will be imperceptible without instruments. The cosmic microwave background, that faint glow of ancient light left over from the Big Bang, will begin to warm. Its temperature, currently 2.7 degrees above absolute zero, will rise by a fraction of a degree. This warming is the first hint of what is to come. As contraction continues, the pace accelerates. Gravity grows stronger as distances shrink. What begins as a slow drift becomes a steady fall. 2 billion years after the turning point, galaxies will be closing the gap at thousands of kilometers per second. Galaxy clusters will begin to merge, their halos of dark matter colliding and triggering waves of star formation as gas clouds compress. The universe will enter a period of renewed activity, brighter and more violent than the present day. The sky will fill with light. New stars will ignite by the billions as collapsing space squeezes gas into dense pockets. Black holes at the centers of galaxies will feast on infalling matter, blazing as brilliant quasars. 5 billion years into the contraction, the universe will have shrunk back to roughly its current size, but it will not stop. Momentum carries it inward. Gravity pulls harder with every passing million years. The cosmic web, once stretched thin by expansion, will collapse into dense knots. Voids will disappear, filaments of matter will merge. The large-scale structure of the universe, shaped by billions of years of expansion, will disintegrate. Everything will fall toward everything else, and there will be no force strong enough to stop it. The collisions will come in waves. As the universe shrinks past its current size, galaxies that have been separated for billions of years will begin to merge. The Milky Way and Andromeda, already on a collision course, will meet long before the Big Crunch. Their encounter, scheduled for roughly 4 billion years from now in the expanding phase, will be dwarfed by the galactic traffic jams that follow. In a contracting universe, mergers accelerate. Every galaxy will eventually collide with every other galaxy within its region of space. The cosmic web will dissolve into a chaotic tangle of merging systems. Galaxy collisions are not gentle. When two galaxies approach, their dark matter halos interpenetrate first, passing through each other like ghosts because dark matter interacts only through gravity. But the gas clouds within those galaxies crash together violently. The collision compresses the gas, heating it to millions of degrees and triggering shock waves that ripple through the interstellar medium. Where the density peaks, new stars ignite by the millions, forming brilliant clusters that blaze across the visible spectrum. These starburst events can produce more stars in a few million years than a quiet galaxy forms in a billion. As the universe continues to contract, the pace of mergers intensifies. Galaxies that collide merge into larger structures, and those structures collide with others, creating supergalaxies that dwarf anything visible today. Black holes at the centers of these galaxies spiral inward as the systems merge, eventually colliding and releasing gravitational waves powerful enough to ripple through space-time. These black hole mergers grow more massive with each iteration. A black hole that weighs 10 million suns merges with another of equal size, forming a 20 million solar mass giant. That giant merges with others, creating monsters weighing hundreds of millions of suns. The sky will become a crowded, violent place. Stars from different galaxies will pass within light years of each other, disrupting planetary systems and scattering objects into chaotic orbits. The density of starlight will increase as the universe shrinks, bathing space in a faint glow that grows brighter with each passing million years. The cosmic microwave background, now invisible to the naked eye, will shift into infrared and then visible light. The universe will glow softly at first, a uniform amber haze filling the void between stars. As contraction accelerates, the glow will brighten and shift toward blue. 8 billion years after the turning point, the universe will have collapsed to half its maximum size. By this stage, galaxy clusters will have merged into vast superclusters containing trillions of stars. The gaps between these structures will have closed. The universe will resemble a dense soup of matter and radiation, far hotter and brighter than it is today. Stars will burn faster as the ambient temperature climbs, exhausting their fuel in millions of years rather than billions. New stars will continue to form from collapsing gas clouds, but their lifetimes will be fleeting. The era of stable stellar systems will be ending. The universe will be transforming into something unrecognizable, a furnace where matter and energy mix in violent equilibrium, racing toward the final collapse. The stars will not survive. As the universe contracts and the cosmic microwave background heats up, every star in the cosmos will face a deadly external pressure. Right now, stars radiate their heat into the cold void of space, maintaining equilibrium between the fusion burning in their cores and the energy escaping through their surfaces. But in a collapsing universe, the background temperature rises. Space itself becomes hot. When the ambient radiation reaches the surface temperature of a star, that star can no longer cool. It begins to cook from the outside. The smallest stars will die first. Red dwarfs, the cool, dim embers that burn hydrogen so slowly they could last trillions of years in a cold universe, will be overwhelmed when the cosmic microwave background reaches a few thousand degrees. This will happen roughly 500,000 years before the Big Crunch in models that trace the collapse in detail. The external radiation will heat their surfaces faster than fusion can sustain them. Unable to radiate away the energy, they will swell and evaporate, their outer layers boiling into space. Within a few thousand years, every red dwarf in the universe will be gone. As the background temperature continues climbing, hotter stars meet the same fate. Orange stars evaporate next, then yellow stars like the Sun. By the time the cosmic microwave background reaches 10,000 degrees, roughly 100,000 years before the end, even the hottest blue giants will begin to boil away. The universe will be filled with expanding clouds of stellar plasma, gas heated to millions of degrees, glowing so brightly that space itself shines. The distinction between stars and the void around them will blur. Everything will be luminous. In the final years, only black holes and the densest neutron stars will remain intact. These objects are so compact that gravity holds them together against any external pressure. But even they will not escape. As the universe collapses toward its final size, black holes will merge at an accelerating pace. Every black hole will eventually encounter another, spiraling inward and colliding in bursts of gravitational waves. The largest black holes, supermassive monsters weighing billions of suns, will devour everything within reach. Gas clouds, stellar remnants, and smaller black holes will plunge into their event horizons, adding mass and growing larger with each meal. In the last million years, the universe will be dominated by a handful of titanic black holes, surrounded by a sea of radiation so intense that atoms cannot exist. The temperature will climb past millions of degrees, then billions. Nuclei will shatter into protons and neutrons. Protons and neutrons will dissolve into quarks and gluons. The universe will resemble the conditions that existed a microsecond after the Big Bang, but in reverse, a fireball collapsing instead of expanding. And as space shrinks faster and faster, even the black holes will merge into a single gravitational abyss. The stars, those engines of light that defined the cosmos for billions of years, will be gone. Only the singularity remains. The universe will become a furnace. As space collapses, the cosmic microwave background, that faint whisper of ancient light left over from the Big Bang, will compress and heat. Right now, it glows at a temperature of 2.7 degrees above absolute zero, invisible to the naked eye, detectable only through radio telescopes. But in a contracting universe, the wavelength of this radiation shortens, the energy concentrates, the temperature climbs, and there is no way to stop it. The heating follows a simple law of physics. When you compress a gas, it warms. The same principle applies to radiation. As the universe shrinks, the photons of the cosmic microwave background gain energy. They blueshift, moving from radio waves toward infrared, then visible light, then ultraviolet. The temperature rises in direct proportion to how much space contracts. If the universe shrinks to half its current size, the background radiation temperature doubles. If it shrinks to a tenth of its size, the temperature multiplies by 10. The relationship is linear, relentless, and unstoppable. 10 billion years after the turning point, with the universe roughly 40% smaller than its maximum size, the cosmic microwave background will reach room temperature. Space itself will feel warm. A billion years later, it will exceed the boiling point of water. Planets still orbiting their stars will begin to cook. Atmospheres will evaporate. Oceans will boil away. Ice caps on distant moons will melt and vaporize. Any life that has somehow survived the galactic mergers and collapsing stars will face an environment hostile beyond imagination. As the collapse accelerates, the temperature soars past thousands of degrees. The cosmic microwave background shifts into visible light, bathing the universe in a uniform glow. Space becomes luminous. The distinction between the void and the objects within it blurs. Everything is immersed in radiation so intense that it overwhelms the light from stars. By the time the background reaches 10,000 degrees, roughly 100,000 years before the Big Crunch, even the hottest stars begin to evaporate. Their surfaces boil into space, unable to radiate heat faster than the external radiation heats them. In the final 1,000 years, the temperature climbs past millions of degrees. Atoms disintegrate. Electrons strip away from nuclei, creating a plasma sea where matter and radiation mix indistinguishably. The universe resembles the conditions that existed microseconds after the Big Bang, but in reverse. As the temperature exceeds billions of degrees, atomic nuclei shatter into protons and neutrons. Then protons and neutrons dissolve into quarks and gluons. The four fundamental forces of nature, which separated as the early universe cooled, begin to merge back together. In the final moments, the temperature approaches infinity. Space collapses faster than light can travel. Time itself warps beyond recognition. The universe becomes a singularity of infinite density and infinite heat, a mirror of the Big Bang, the end that looks like the beginning. The Big Bang was not creation. It was a transition, a moment when something already in motion changed phase. This is the insight at the heart of ekpyrotic cosmology, a model that extends time infinitely backward and forward, erasing the concept of a beginning. Our universe did not emerge from nothing. It emerged from a collision between higher dimensional objects called brains, vast membranes floating in a space we cannot see, governed by forces we do not experience. The Big Bang was the impact, the moment when two brains crashed together and released energy into our three dimensions. The ekpyrotic model solves problems that standard cosmology struggles with. One of these is the horizon problem, the fact that the cosmic microwave background looks the same in all directions, even though those regions were never in contact during the early universe. If the universe started 13.8 billion years ago, and nothing travels faster than light, distant parts of the sky should not have the same temperature. They never had time to exchange energy and reach equilibrium. Inflation, the rapid expansion that supposedly happened a fraction of a second after the Big Bang, was invented to solve this. But inflation requires fine-tuning and exotic physics that have never been observed. Ekpyrotic cosmology offers an alternative. Instead of a universe that inflates from a hot dense point, it proposes a universe that contracts slowly from a large cold state before the Big Bang. During this contraction, different regions of space have time to interact and smooth out their differences. By the time the brains collide and the Big Bang happens, the universe is already uniform. The horizon problem disappears. The flatness problem, the mystery of why space has zero curvature, also disappears. A slowly contracting universe naturally flattens itself through gravitational interactions. No inflation required. The collision itself is violent but brief. When the brains touch, they convert their kinetic energy into heat and particles. This is what we see as the Big Bang, a sudden flood of radiation and matter filling three-dimensional space. But the brains themselves are not destroyed. They bounce apart, drifting back into the higher dimensional space they came from. For billions of years, they separate, and the universes on their surfaces expand and cool. Stars form, galaxies cluster, complexity emerges. Then, slowly, forces in the extra dimensions pull the brains back together. They accelerate toward each other. Eventually they collide again. Another Big Bang, another cycle. In this framework, the Big Crunch is not the end. It is the prelude to the next beginning. As our universe contracts and heats, approaching the singularity, quantum effects become dominant. At extremely high densities, space-time itself becomes uncertain, fluctuating wildly on the smaller scales. Some models suggest that these quantum fluctuations generate a repulsive force, a kind of anti-gravity that halts the collapse and reverses it into a new expansion. The singularity never forms. Instead, the universe bounces, transitioning smoothly from Big Crunch to Big Bang. Time does not end. It continues, carrying the universe into the next cycle. There was a universe before this one. It expanded, aged and collapsed just as ours might. Stars formed and died, galaxies merged, black holes swallowed matter and radiated energy. Eventually the expansion slowed, stopped and reversed. Space contracted. The temperature climbed. Everything fell back together. But instead of ending in a singularity where time ceased and physics broke, the universe bounced. Quantum effects halted the collapse at the last moment, reversing the contraction into a new expansion. That expansion became our Big Bang. This is the Cyclic Universe model, first proposed by Paul Steinhardt and Neil Turok in 2001. It describes an endless sequence of cosmic epochs, each lasting tens of billions of years. Each cycle includes a phase of slow expansion driven by dark energy, followed by a period of slow contraction driven by gravity. The transition from contraction to expansion happens smoothly. The temperature and density remain finite throughout. There is no singularity, no moment when the laws of physics fail. The universe simply bounces, like a ball hitting the ground and rebounding into the air. The bounce is not random. It emerges naturally from the physics of the contracting phase. As the universe shrinks, matter and radiation become denser and hotter. But before the density reaches infinity, quantum corrections to gravity become important. These corrections create a repulsive force that grows stronger as space contracts. Eventually, the repulsion overwhelms gravity and halts the collapse. The universe stops shrinking and begins expanding again. This transition happens in a fraction of a second, but it is smooth and controlled. No singularity forms. The previous cycle would have looked much like ours. It had stars, galaxies, planets, and perhaps even life. It lasted for billions of years, long enough for complexity to emerge and evolve. But as dark energy weakened and gravity took over, the expansion slowed and reversed. Galaxies began falling back together. Stars burned out as the cosmic microwave background heated up. Black holes merged into larger and larger objects. In the final moments, space contracted to a size smaller than an atom, compressing all the matter and energy in the universe into a dense fireball. Then, the bounce happened. The fireball exploded outward, becoming the Big Bang we observe. The beauty of this model is that it solves problems the standard Big Bang cannot. The horizon problem, the fact that distant parts of the universe have the same temperature, even though they were never in contact, disappears because the contracting phase before the Big Bang gave those regions time to interact. The flatness problem, the mystery of why space has zero curvature, disappears because a slowly contracting universe naturally flattens itself through gravitational smoothing. The model also explains why the universe is so uniform, why it contains the amount of matter and energy we observe, and why the density fluctuations that seeded galaxies have the pattern they do. All of these features were set up during the previous cycle, not during a brief inflationary epoch that requires exotic physics. We cannot see past the Big Bang, the moment of the bounce, when the previous universe collapsed and rebounded into ours, erases its own history. This is the cosmic amnesia, the fundamental barrier that prevents us from observing what came before. The reason is simple. During the collapse phase, temperatures and densities climb so high that matter breaks down into its most elementary constituents. Atoms dissolve into quarks and leptons. Even the fabric of space-time becomes uncertain, fluctuating wildly under quantum effects. By the time the bounce occurs, all the complex structures that defined the previous universe have been obliterated. The Big Bang itself acts as a wall. When we look back in time using telescopes, we see light from galaxies billions of years old, ancient structures formed when the universe was young. The farthest we can see is the cosmic microwave background, light emitted 380,000 years after the Big Bang, when the universe cooled enough for atoms to form. Before that moment, space was opaque, filled with a hot plasma that scattered photons in every direction. No light from earlier times can reach us, and no light from a previous cycle can survive the bounce. The radiation is diluted, redshifted, and absorbed as space contracts. By the time the new cycle begins, nothing remains. But the cosmic microwave background might carry faint clues. Roger Penrose's conformal cyclic cosmology predicts that certain features from the previous universe could leave imprints, specifically supermassive black holes from the prior cycle, as they evaporate through Hawking radiation in the final moments before the bounce, would release bursts of energy. These bursts, concentrated and amplified during the transition between cycles, could appear in our universe as unusual hotspots in the cosmic microwave background. Penrose calls them Hawking points. In 2018, Penrose and his collaborators claimed to have found these hotspots in data from the Planck satellite. They identified small circular patches in the cosmic microwave background, where the temperature gradient was unusually steep, roughly 10 times higher than the average fluctuation. They compared these patches to simulations based on the standard Big Bang model and found that none of the simulations produced similar features. Penrose argued this was evidence for conformal cyclic cosmology, proof that our universe is not the first, but one stage in an infinite sequence. The scientific community remains skeptical. Other researchers have pointed out that the analysis may suffer from statistical flaws, particularly the look elsewhere effect, where patterns emerge by chance when you search through large data sets. Douglas Scott, a cosmologist at the University of British Columbia, described the paper as muddled and unconvincing. James Zibin, another skeptic, noted that scientists have been scrutinizing the cosmic microwave background for decades and have found no definitive evidence for unusual hotspots beyond what random chance would produce. The debate continues. Future observations from next-generation telescopes may settle the question, revealing whether the universe truly cycles or whether the Big Bang marks an absolute beginning. For now, the past remains hidden, locked behind the wall of fire that is the Big Bang. The universe might never truly die. Instead of collapsing into a singularity where time ends and nothing can exist, it could bounce and begin again, repeating this process endlessly across infinite time. Each cycle would last tens of billions of years, long enough for stars to form, galaxies to evolve, and complexity to emerge. Then dark energy would weaken, gravity would dominate, and the universe would contract. But instead of crushing everything into oblivion, quantum effects would halt the collapse and reverse it. The crunch becomes a bang. A new cycle begins. This is not the old idea of an oscillating universe that simply repeats itself identically. Modern cyclic models allow each cycle to be different. The scale factor, the number that describes how much the universe has expanded since the Big Bang, grows larger with each bounce. Entropy, the measure of disorder, increases from one cycle to the next. Black holes form during each cycle, evaporating slowly through Hawking radiation, and their remnants seed the structure of the next cycle. This means the universe evolves across cycles, never returning to exactly the same state. Time stretches infinitely in both directions, past and future, with no beginning and no end. Paul Steinhardt and Anna Ayers have developed a particularly elegant version of this model. Their cyclic universe undergoes slow contraction followed by a bounce and then slow expansion. Dark energy drives the expansion initially, but as it weakens, the universe enters a long phase of gradual cooling. During this phase, matter clumps into galaxies, stars ignite, planets form, and life becomes possible. Eventually, gravity overcomes dark energy, and contraction begins. The universe shrinks slowly, heating as it does so, until quantum effects trigger the bounce. The key difference from earlier models is that the scale factor increases exponentially from one cycle to the next. Each new cycle is larger and lasts longer than the previous one. This growth solves a critical problem that plagued older cyclic models: entropy. The second law of thermodynamics states that entropy always increases. In a repeating universe, entropy would accumulate over time, eventually filling each cycle with so much disorder that stars could not form and complexity could not emerge. The universe would die not in a single cataclysmic collapse, but through gradual degradation across endless cycles. But if the scale factor grows exponentially, the universe dilutes its entropy. Each new cycle starts with more space, spreading the disorder thinner. This allows stars, galaxies, and life to form again and again without limit. The model makes predictions that future observations can test. Cyclic universes produce gravitational waves with a specific spectrum, different from what inflation predicts. These waves, generated during the bounce, would leave imprints in the polarization patterns of the cosmic microwave background. Next-generation telescopes designed to measure these patterns, such as the Lightbird satellite and the Simons Observatory, should be able to detect or rule out the signature. If the cyclic model is correct, the universe has no beginning. It has always existed and always will, cycling eternally through birth, death, and rebirth. The cyclic universe makes testable predictions. Unlike purely philosophical ideas about infinite time, this model stakes its survival on observations that future telescopes can measure. The clearest test involves gravitational waves, ripples in space-time generated during the earliest moments of cosmic history. Inflation, the rapid expansion supposed to have happened microseconds after the Big Bang, produces gravitational waves with a specific pattern. These waves should leave imprints in the polarization of the cosmic microwave background, creating swirling patterns in the ancient light. If those patterns exist, inflation wins. If they do not, the cyclic model gains ground. The difference comes down to violence versus gentleness. Inflation is fast and explosive, compressing trillions of years of expansion into a fraction of a second. This generates powerful gravitational waves that ripple through the universe. The cyclic model, by contrast, involves slow contraction followed by a gentle bounce. The process takes billions of years, not microseconds, and it is too mild to produce detectable gravitational waves. Paul Steinhardt describes the contrast vividly. Inflationary fluctuations are violent enough to shake space-time. Cyclic fluctuations are ultra-slow and quiet, leaving no gravitational signature. Current telescopes cannot yet resolve this question. The polarization patterns from primordial gravitational waves are incredibly faint, buried in noise from foreground sources like dust in our galaxy. But next-generation instruments are being built specifically to hunt for them. The Lightbird satellite, scheduled to launch later this decade, will map the polarization of the cosmic microwave background with unprecedented precision. The Simons Observatory and CMB Stage 4, ground-based experiments under construction in Chile, will do the same. Within 10 to 15 years, these missions will either detect the gravitational wave signature of inflation or rule it out. If they rule it out, cyclic cosmology becomes the leading explanation for the origin of the universe. There are other hints, though more controversial. Roger Penrose claims that unusual hotspots in the cosmic microwave background could be remnants of black holes from the previous cycle. These Hawking points, as he calls them, would appear as small circular patches where the temperature gradient is much steeper than expected. In 2018, Penrose and his collaborators reported finding such features in data from the Planck satellite. They analysed small regions of the sky and compared the temperature variations to simulations based on standard cosmology. In many cases, the real data showed temperature gradients an order of magnitude higher than any simulation predicted. The scientific community remains divided. Critics argue that the analysis may be flawed, that statistical artifacts can masquerade as real patterns when you search through large data sets. Douglas Scott, a cosmologist at the University of British Columbia, called the paper muddled and unconvincing. James Zibin, another skeptic, noted that the odds of finding such hotspots by chance might be as high as 1 in 50 once you account for the multiple tests performed. But Penrose stands by the result. He welcomes alternative explanations but argues that matching the observed temperature gradients within the standard model will require radically new ideas. The debate continues. Future missions with better resolution and sensitivity may settle it. The evidence is mounting and the sky holds the answer. We are caught between endings. The universe is 13.8 billion years old, approaching the halfway point of its total lifespan if the Big Crunch models are correct. Dark energy dominated cosmic expansion for the last 4 billion years, but its grip is weakening. The latest data from the Dark Energy Spectroscopic Instrument shows that its density has dropped by 10% over the past 4.5 billion years. If this trend continues, expansion will slow, stop, and reverse within the next 11 billion years. We live in the age of transition, the moment when the universe pivots from acceleration to deceleration, from the age of stars to the prelude of collapse. The evidence is compelling but not yet definitive. The statistical confidence for evolving dark energy stands at 4.2 sigma, meaning the odds of seeing this pattern by chance if the standard model were correct are roughly 1 in 30,000. That is strong, but it falls short of the 5 sigma threshold that physicists demand for claiming a discovery. Multiple independent datasets point in the same direction. The cosmic microwave background shows it. Supernovae confirm it. Gravitational lensing supports it, but uncertainties remain. Some models suggest dark energy could stabilize at a small positive value, allowing the universe to expand forever at a diminishing rate. Others predict it will plunge below zero, becoming attractive and accelerating the collapse. A recent analysis published in Physical Review D examined the latest data and found a 93.8% preference for a future transition into anti-de Sitter space, a state where dark energy becomes negative and drives contraction. This does not guarantee a big crunch, but it makes collapse far more likely than the heat death. The timeline remains uncertain. Henry Tye's model predicts the universe will reach maximum size 11 billion years from now and collapse to a singularity 9 billion years after that. Other models extend the timeline by tens of billions of years, but all models incorporating weakening dark energy point toward the same conclusion: the universe will not expand forever. If the cyclic models are correct, this is not the first time the universe has gone through this process. A recent theoretical study incorporating information theory into cosmology estimates that the universe has already cycled through 3 or 4 expansions and contractions. The model suggests that fewer than 10 cycles remain before the informational capacity of space-time becomes fully saturated. After that, no further bounces occur. Instead, the universe enters a final phase of slowing expansion that continues indefinitely. This would place us in the late stages of cosmic history, living during one of the last cycles before the bounces stop. We stand at a unique moment. The fate of the universe is no longer abstract philosophy. It is physics, testable and falsifiable, waiting for telescopes to measure the answer. Within the next decade, next-generation instruments will determine whether dark energy continues weakening, stabilizes, or behaves in ways we have not anticipated. The Dark Energy Spectroscopic Instrument will complete its final survey by late 2026 or early 2027, mapping 50 million galaxies and tracing the expansion history with unprecedented precision. The European Euclid satellite and NASA's Nancy Grace Roman Space Telescope will add their own measurements. Together, these missions will reveal which fate is ours, and we will know, for the first time in human history, how the universe will end. The universe has been lying to us. For over a decade, 2 different methods for measuring cosmic expansion have produced 2 incompatible answers. When astronomers look at the early universe using the cosmic microwave background, they calculate an expansion rate of 67 kilometers per second per million light-years. When they measure nearby galaxies using supernovae, they get 73. This 9% difference became known as the Hubble tension, and it refused to go away. More precise measurements only made it worse. Either one method was wrong, or something fundamental was missing from cosmology. Weakening dark energy solves the problem. If dark energy's density has been dropping over time, the expansion rate measured in the early universe would differ from the rate measured in the nearby universe. The cosmic microwave background shows us the universe as it was 13 billion years ago when dark energy was stronger. Supernovae show us the universe over the last few billion years when dark energy has weakened. The 2 methods are both correct. They simply measure expansion at different times when dark energy had different strengths. The Hubble tension is not an error. It is evidence that dark energy evolves. This realization changes everything. For years, cosmologists assumed the tension meant something was wrong with their measurements. They recalibrated instruments, checked for systematic errors, and reanalyzed data. Some proposed radical fixes such as introducing new particles or modifying gravity itself. But the simplest explanation was staring them in the face. Dark energy is not constant. It weakens over cosmic time. When you incorporate this into the models, the tension disappears. Both measurements agree. The implications ripple outward. If dark energy weakens, the universe cannot expand forever. The heat death is off the table. The big crunch becomes plausible. The timeline Henry Tye calculated, with the universe reaching maximum size in 11 billion years and collapsing 9 billion years later, suddenly fits all the observational data. The negative cosmological constant that seemed so strange when Tye first proposed it now explains not just the future, but the present. It explains why expansion is slowing. It explains why the Hubble tension exists. It explains why the universe appears to be transitioning into a new phase. The resolution is elegant but unsettling. Cosmology spent decades building a consensus around the standard model, a framework where dark energy was constant and expansion was eternal. That consensus is crumbling. The latest data from the Dark Energy Spectroscopic Instrument, combined with independent observations from Young-Wook's team and the analysis that resolved the Hubble tension, all point toward the same conclusion. Dark energy is changing, the universe is slowing down, and the end, once thought to be trillions of years away, could arrive in 20 billion. The Hubble tension was not a problem to solve. It was a message from the cosmos, telling us the future is closer than we thought. Life exists because the universe is dying slowly. If expansion continued forever at an accelerating rate, galaxies would drift apart until each became isolated in its own bubble of space. The cosmic horizon would shrink around every star system, cutting them off from the rest of reality. If the universe collapsed quickly, galaxies would never form. Matter would rush back together before gravity had time to clump gas clouds into stars. Only a universe that expands for a specific period, then contracts over a longer timescale, allows complexity to emerge. Only in that narrow window can atoms assemble into molecules, molecules into cells, cells into civilizations. We live in the Goldilocks zone of cosmic history. The universe is 13.8 billion years old, roughly halfway to its maximum size. Stars have been forming for 13 billion years, long enough for heavy elements to accumulate through generations of stellar evolution. Planets orbit those stars in stable systems where liquid water can persist for billions of years. Life had time to begin, evolve, and reach intelligence, but this window will not stay open forever. In a universe heading toward the Big Crunch, the future narrows. 11 billion years from now, expansion will stop. The contraction phase begins. For the first few billion years of collapse, life could still thrive. Galaxies will drift closer together, but stars will continue to form and planets will remain stable. The night sky will grow brighter as galaxies merge, but the changes will be gradual enough for civilizations to adapt. 10 billion years into the contraction, however, conditions will begin to deteriorate. The cosmic microwave background will heat up, warming space itself. Planets will bake, stars will burn faster as external radiation adds to their internal energy. Eventually, the temperature will climb so high that complex molecules cannot exist. The final billion years will be uninhabitable. By that point, the universe will resemble a furnace. Space will glow with visible light. The temperature will exceed thousands of degrees. No planet could sustain an atmosphere. No star could cool itself. Matter itself will begin to dissolve as atoms break apart under the relentless heat. Any civilization that survives to witness this era will face extinction not from local catastrophe, but from the collapse of the cosmos itself. There will be no escape. No corner of the universe will remain cool. The Big Crunch is absolute. If the cyclic models are correct, life might return. After the bounce, a new universe expands and cools. Stars form again, galaxies cluster, planets coalesce from dust and gas. Life emerges, not as a continuation of what came before, but as a fresh beginning. The cycle repeats, offering infinite opportunities for complexity across infinite time. But each individual cycle is finite. Life flourishes only during the narrow window between the early chaos of the Big Bang and the final inferno of the Big Crunch. We are living in that window now, witnesses to a cosmic drama that has played out before and will play out again. They will see the sky change first. Civilizations living 15 billion years from now, long after humanity has vanished, will watch galaxies drift closer together instead of farther apart. The blueshift will be subtle at first, detectable only through precise spectroscopy. But over millions of years, the effect will become unmistakable. Galaxies once separated by hundreds of millions of light years will merge. The night sky will grow brighter as star systems crowd together. Astronomers will realize that the universe has entered its final phase. For billions of years, life could continue. The contraction would proceed slowly enough that solar systems remain stable. Stars would keep burning, planets would orbit normally, and the cosmic microwave background would remain cold enough to be invisible. Advanced civilizations might even find ways to adapt, migrating to regions of space less affected by the mergers, or building habitats shielded from the increasing radiation. But the collapse is inevitable. No technology can reverse it. The forces driving the universe back together are woven into the fabric of space-time itself. 10 billion years into the contraction, the warnings will become urgent. The cosmic microwave background will heat past the freezing point of water, then past the boiling point. Space itself will feel warm. Planets without thick atmospheres will begin to overheat. Ice caps on distant moons will melt and vaporize. Life will retreat to the coldest corners of the universe, sheltering in the shadows of massive objects or deep underground where temperatures remain tolerable. But the heat will follow. The background radiation will continue climbing, shifting from infrared into visible light. The void between stars will glow. In the final billion years, survival becomes impossible. The temperature will exceed thousands of degrees, atmospheres will boil away, oceans will evaporate, even the hardiest life forms, those adapted to extreme heat or radiation, will find no refuge. The universe will resemble the interior of a star. Matter will exist only as plasma, particles stripped of electrons and smashed together by the relentless pressure of collapsing space. Any intelligence that has managed to endure will witness the dissolution of reality itself. Stars will evaporate, planets will vaporize, galaxies will merge into a single luminous cloud. The very last observers, if any exist, will see the end approach with terrifying clarity. Space will collapse faster than light can travel. The horizon will shrink around them, cutting off distant regions one by one. The cosmic microwave background will blueshift into X-rays and gamma rays, bathing everything in lethal radiation. Atoms will disintegrate, nuclei will shatter. The four fundamental forces will begin to merge back together, and then, in a flash briefer than a heartbeat, space will compress to zero volume. Time will end. The singularity will consume everything. There will be no survivors, no records, no memory of what came before. Just the bounce, the explosion outward into a new cycle, where new stars ignite and new life begins, ignorant of the universes that came before. The crunch might not be the end. It might be the doorway to the next beginning. If quantum effects halt the collapse before the singularity forms, the universe bounces instead of dying. The infinite density never arrives. The infinite temperature never happens. Instead, space reaches a minimum size, perhaps as small as the Planck length, and then rebounds violently outward. The big crunch becomes the big bang of the next cycle. The phoenix rises from its ashes. This transition solves the singularity problem that haunts classical cosmology. General relativity, Einstein's theory of gravity, predicts that collapsing space will compress to a point of infinite curvature where the laws of physics break down. At that point, the equations produce nonsense. Time stops, space disappears, nothing can exist. But quantum mechanics, the theory governing the smallest scales, offers a way out. At extremely high densities, quantum fluctuations in space-time become violent. These fluctuations generate a repulsive force, a kind of quantum pressure that resists further compression. When the density climbs high enough, this pressure overwhelms gravity and reverses the collapse. The bounce happens fast. According to models that incorporate quantum corrections to general relativity, the universe contracts to roughly 1.7 times the Planck length, a distance so small that 10 trillion of them would fit across a single proton. At that scale, spacetime itself becomes uncertain, fluctuating wildly between different geometries. The repulsive quantum force builds rapidly as the universe shrinks, eventually becoming strong enough to halt the collapse in a fraction of a second. Then, the rebound begins. Space explodes outward with the same violence that characterized the Big Bang. Energy floods into 3 dimensions. Particles form from the vacuum. The temperature drops as expansion cools the fireball. Within microseconds, the new universe looks identical to the one we observe around us. The information from the previous cycle is mostly erased. Structures like galaxies, stars, and planets cannot survive the extreme conditions near the bounce. They dissolve into elementary particles long before space reaches its minimum size. But some features persist. Black holes from the previous universe may leave imprints in the cosmic microwave background of the new one. The total entropy, the measure of disorder, carries over and continues increasing from one cycle to the next. The scale factor, which describes how much the universe has expanded, grows larger with each bounce. This means each new cycle is bigger than the last, lasting longer, and producing more stars before gravity pulls it back together. If this model is correct, our universe is not the first and will not be the last. It emerged from the collapse of a previous cosmos that was smaller, shorter-lived, and perhaps slightly different in its physical constants. When our universe reaches the big crunch in 20 billion years, it will bounce and become the next cycle. That new universe will expand, cool, and form galaxies of its own. Stars will ignite, planets will coalesce, and perhaps life will emerge again, ignorant of the cycles that came before. The process repeats endlessly, a phoenix universe that dies and is reborn across infinite time. We will not have to wait forever for the answer. Within the next decade, telescopes will determine whether the universe cycles or dies. The evidence will come from gravitational waves, ripples in space-time generated during the earliest moments of cosmic history. If inflation happened, if the universe exploded from a singularity in a fraction of a second, those gravitational waves should have left imprints in the polarization of the cosmic microwave background. If the cyclic model is correct, if the universe contracted slowly before bouncing into expansion, no such imprints exist. The distinction is clear, the observations are feasible, and the missions are already being built. The Lightbird satellite, scheduled for launch in the late 2020s, will map the polarization patterns of the cosmic microwave background with unprecedented sensitivity. The Simons Observatory and CMB Stage 4, ground-based experiments under construction in Chile's Atacama Desert, will do the same from Earth. Together, these instruments will search for the signature of primordial gravitational waves. If they find it, inflation wins and the cyclic model fails. If they do not, the cyclic model becomes the leading explanation for the origin and fate of the universe. Paul Steinhardt, one of the architects of cyclic cosmology, describes the stakes plainly. Within 10 to 15 years, we will know which theory is correct. The scientific community remains divided. Many cosmologists favour inflation because it solves problems that the standard Big Bang cannot explain, such as why the universe is so uniform and why space is flat. But inflation requires exotic physics, fields and forces that have never been observed. The cyclic model offers an alternative, explaining the same features through a phase of slow contraction before the Big Bang. This contraction smooths out irregularities naturally, without invoking unknown particles or energies. The debate has simmered for 2 decades, but it is about to be resolved. Roger Penrose's conformal cyclic cosmology adds another layer to the question. His model predicts that supermassive black holes from the previous cycle leave imprints in our cosmic microwave background, appearing as unusual hotspots with steep temperature gradients. In 2018, Penrose claimed to have found these Hawking points in data from the Planck satellite. The scientific community remains skeptical, arguing that the analysis may be flawed or that the patterns could arise by chance. But Penrose stands by the result. Future missions with better resolution will either confirm or refute his claim. The timeline is converging. The Dark Energy Spectroscopic Instrument will complete its survey by 2027, determining whether dark energy continues weakening or stabilizes. The European Euclid satellite and NASA's Nancy Grace Roman Space Telescope will measure cosmic expansion with unprecedented precision, revealing whether the universe is heading toward collapse or eternal expansion. The gravitational wave detectors will search for the signature of inflation or the absence that favours cyclic cosmology. Within a decade, these missions will converge on a single answer. We will know how the universe began, whether it will end, and if it has done this before. The verdict is coming. 27 years ago, we discovered the universe was accelerating. The finding won a Nobel Prize and reshaped cosmology. Dark energy was real, powerful, and seemingly eternal. The fate of the cosmos seemed settled. The universe would expand forever, cooling into a frozen void where stars burn out and galaxies drift beyond reach. The heat death was inevitable. Now, in 2025, that certainty is gone. Dark energy is weakening, the expansion is slowing, and the future we thought we understood has dissolved into uncertainty. The data comes from multiple independent sources, and they all tell the same story. The Dark Energy Spectroscopic Instrument mapped 15 million galaxies across 11 billion years of cosmic history. The patterns in their distribution reveal ancient sound waves frozen into space, cosmic rulers that measure how the universe has expanded over time. When researchers analysed these patterns, they found that dark energy's density has dropped by 10% over the last 4.5 billion years. This is not noise, it is a signal. Dark energy evolves, and if it continues weakening, the universe will stop expanding. The timeline is staggering. Henry Tye's model, published in 2025, predicts the universe will reach maximum size in 11 billion years, roughly 69% larger than it is today. Then expansion will stop. Contraction will begin. The universe will shrink for another 8 to 9 billion years before collapsing into a singularity. Total lifespan from Big Bang to Big Crunch, 33 billion years. We are currently 13.8 billion years into that journey, approaching the halfway mark. The end, once thought to be trillions of years away, could arrive in 20 billion. This is not the only possibility. Dark energy could stabilize at a small positive value, allowing the universe to expand forever at a decreasing rate. It could behave in ways no current model predicts. The statistical confidence for evolving dark energy is 4.2 sigma, compelling but not definitive. A 5 sigma result, the gold standard for discovery, requires more observations, but those observations are coming. The Dark Energy Spectroscopic Instrument will complete its final survey by 2027. The European Euclid satellite and NASA's Nancy Grace Roman Space Telescope will add their measurements over the next decade. These missions will determine whether dark energy truly weakens, stabilizes, or surprises us. Within 10 years, we will know. We will know whether the universe cycles or dies. We will know whether the Big Bang was the beginning or a transition. We will know whether life can return after the Big Crunch, or whether extinction is final. For the first time in human history, the fate of everything is within reach. The telescopes are built, the missions are launching, the data is arriving, and the universe, after billions of years of silence, is about to tell us how the story ends.